Hello class, today we'll be discussing the second area of statistics, which is the inferential statistics. The purpose of statistical inference is to draw conclusions about a population on the basis of data obtained from a sample of that population. Hypothesis testing is the process used to evaluate the strength of evidence from the sample and provides a framework for making determinations related to that population. That is to provide a method for understanding how reliably one can extrapolate observed findings in a sample under study to the larger population from which the sample was drawn. The researcher formulates a specific hypothesis, evaluates data from the sample, and uses this data to decide whether to support the specific hypothesis. Hypothesis is the assumption or idea that proposes a tentative explanation about a phenomenon or a narrow set of phenomena observed in the natural world. The first step in hypothesis testing is the transformation of the research question into a null hypothesis, usually denoted by H sub O. And this is the hypothesis that must always express the idea of non-significance of difference, lack of association or relationship between the dependent and independent variables. And the alternative hypothesis, which is denoted by H sub A. And this is the opposite of the null hypothesis, for it specifies an existence of a difference, association, or relationship, again, between the dependent and independent variables. The null and alternative hypotheses are concise statements, usually in mathematical form, of two possible versions of truth about the relationship between the predictor of interest and the outcome in the population. These two possible versions of truth must be exhaustive, meaning they should cover all possible truths and mutually exclusive or not overlapping. The alternative hypothesis is typically what the investigator would like to show. The goal of statistical testing is to decide whether there is sufficient evidence from the sample under study to conclude that the alternative hypothesis should be believed. Hypothesis testing has been likened to a criminal trial in which a jury must use evidence to decide which of the two possible truths is to be believed. In statistics, the claim of the defense is called the null hypothesis, denoted by H sub O. It is the hypothesis that is to be tested, which is hoped to be rejected. It is the claim about a population parameter that is assumed to be true until it is proven false. It shows equality, no significant difference, or no relationship between variables. The claim of the prosecutor is called the alternative hypothesis, denoted by H sub A, and it is the hypothesis which the researcher wants to prove. It is a claim about a population parameter that will be true if the null hypothesis is proven false. It shows inequality or a significant difference or relationship between variables exists. Just as a jury is instructed to assume the defendant is innocent unless proven otherwise, the investigator should assume there is no association unless there is strong evidence to the contrary. A jury's verdict must be either guilty or not guilty, in which case a not guilty verdict does not equal innocence. Rather, it indicates that the burden of proof has not been met. Similarly, an investigator can only reject the null hypothesis or fail to reject it. Failure to reject does not prove that the null hypothesis is true. Okay, let us have examples on formulating the null and alternative hypothesis. Let's say the title of a study is The Effects of Online Gaming on the Academic Achievements of Freshman High School Students. What could be the possible null hypothesis given this title? We can state the null hypothesis in this way. Online gaming has no significant effect or effects on the academic achievements of high school freshman students, which means that a possible alternative hypothesis is that online gaming has significant effect or effects on the academic achievements of high school freshman students. Another example, the title is given as The Correlation Between Competencies in English and Mathematics. A possible null hypothesis could be stated that there is no correlation between competencies in English and mathematics. And for the alternative hypothesis, we say that there is a correlation between competencies in English and mathematics. To better understand hypothesis testing, let us discuss some terminology used in this process. Okay, take note that the rejection of null hypothesis implies the acceptance of its alternative, and the acceptance of the null hypothesis implies the rejection of the alternative hypothesis. Since null hypothesis testing is based on sample means and not the population means, there is a possibility of making an error or wrong decision in rejecting or failing to reject the null hypothesis. These two types of errors are known as type 1 error and type 2 error. Type 1 error is when we reject a true null hypothesis, and type 2 error is accepting a false null hypothesis. Type 1 error is usually denoted by alpha error. So again, that is when we reject the null hypothesis when in fact it is true. And type 2 error or beta error is when we accept the null hypothesis when in fact it is false. We also have the so-called level of significance, which is the maximum value of the probability of rejecting the null hypothesis when in fact it is true. Commonly used levels of significance are 1%, meaning there is a 99% confidence level. A 2.5% level of significance implies a confidence level of 97.5%. 5% level of significance, which is usually used, implies a level of confidence of 95%. And a 10% level of significance implies a confidence level of 90%. Test statistic is a function of the random sample that is based on the observations and is used to make the decision in favor of the null or alternative hypothesis. Common examples of test statistics used in hypothesis testing are the t-statistic, z-statistic, f-statistic, and the chi-square. The T and Z statistics or T and Z tests are used when we want to determine if there's a significant difference between two groups, provided that the data are quantitative. F statistic or F test is the one that we use when doing analysis of variance or the ANOVA. ANOVA is a test used when we want to know if there is a significant difference between or among three or more groups. It is also a test used when the data given are quantitative. And the chi-square is a non-parametric test which is used when the data given are in the nominal level. We'll be discussing more of this test statistics in our next lesson. The critical region is a set of values of the test statistic that is chosen before the experiment to define the conditions under which the null hypothesis will be rejected. In statistics, we make decisions based on how far a test statistic deviates from a standard or tabular statistic, which is also called the critical value. It is a value that separates a critical region or the rejection region from the acceptance region in a hypothesis test, usually presented in distribution tables. So there are two regions, the region of non-rejection and the region of rejection. If the test statistic falls in the region of non-rejection, the null hypothesis should not be rejected. If, on the other hand, the test statistic falls in the rejection region, the null hypothesis is rejected. Again, to reject the null hypothesis means to conclude that the null hypothesis is false. And to not reject or accept the null hypothesis merely implies that there is no sufficient evidence to believe that it is false. A one-tailed test is used when the critical region is located at only one extreme of distribution or range of values for the test statistic. A one-tailed test is appropriate for a directional hypothesis. A two-tailed test is used when the critical region is located on both sides of the distribution or range of values for the test statistic. So this one is applied to non-directional hypothesis. The degrees of freedom, or DF, refers to the number of free choices that can be made. So this figure here shows 5% region of rejection of null hypothesis that is non-directional. So this is for a two-tailed test, wherein the region of rejection are on both extreme sides of the distribution. And then for a one-tailed test, we have here the 5% region of rejection of null hypothesis that is directional. So these are the suggested steps in hypothesis testing. So this is for determining difference, if there's a significant difference that exists between two groups. So first, we formulate the null hypothesis, or H sub O, and the alternative hypothesis, H sub A, which is used in case the null hypothesis is rejected. Second step is to set the level of significance, or that is a value of alpha, and determine the direction of the test. Third is to determine the test statistic to be used. Note that in testing the difference between two means of two groups, the z-test or t-test may be used. The z-test is used when the population standard deviation is known or given, while the t-test is used when the standard deviation is from the sample. So again, we apply either the z-test or t-test if we want to determine if there's a significance between two groups in terms of their mean. So that also implies that the data must be quantitative, either ratio or in the interval level of measurement. Next step is to determine the tabular value of either the z or the t-test. So we use the table of the critical values of z based on the area of the normal curve. For a t-test, we compute first for the degrees of freedom, then look for the tabular value from the table of t distribution. For a single sample, the degrees of freedom is equal to the sample size n minus 1. And for two samples, the degrees of freedom is equal to n sub 1 plus n sub 2 minus 2. So these are the sample sizes of the two groups. The next step is to compute for z or t as needed using the appropriate formula. Number 6, compare the computed value with its corresponding tabular value, then state your conclusion based on the following guidelines. So these are the criterion whether or not to reject the null hypothesis. So we reject the null if the absolute computed value is equal to or greater than the absolute tabular value. So the tabular value is also called the critical value. And we accept the null hypothesis if the absolute computed value is less than the absolute tabular value. And then the last one is to draw or state the conclusion. So this is based on the hypothesis that is not rejected. Another decision rule is based on the so-called p-value. So the p-value, if alpha is greater than 0.05, we do not reject the null hypothesis. But if the alpha or the p-value, which is denoted by the significance level, is equal to or less than 0.05, we reject the null hypothesis. This next slides will show you the different statistical test formulas for both the z-test and the t-test. So the first one is the formula that we use given a sample mean compared with a population mean. So the computed z value is equal to the difference of the sample mean and the population mean multiplied by the square root of the sample size divided by the population standard deviation. So again, we use the z-test if we know the population standard deviation. Another formula for z is when comparing two sample means. So z is equal to the difference of the two sample sizes, x sub 1 and x sub 2, divided by the population standard deviation multiplied by the square root of 1 over n sub 1 plus 1 over n sub 2. And then this one is the last formula under the z-test. So this is used when comparing two sample proportions, wherein z is equal to the difference of the two proportions, p sub 1 and p sub 2, divided by the square root of p sub 1 times q sub 1 divided by n sub 1 plus p sub 2 times q sub 2 divided by n sub 2, wherein q sub 1 is 1 minus p sub 1 and q sub 2 is 1 minus p sub 2. P sub 1 and p sub 2 are the proportions of the two samples. And then These are the formulas for T when performing t-tests. So the first one is applied when a sample mean is compared with the population mean. So we use t-tests if the standard deviation is derived from the sample. So for the first formula, T is equal to the difference of the sample mean and the population mean mu multiplied by the square root of n minus 1. So n is the sample size all over the sample standard deviation S. And then for the second formula of T is used when comparing two sample means. So T is equal to, so this formula is longer than the others, no? So T is equal to the difference of the two sample sizes, two sample means divided by the square root of, so we have the first sample size minus 1 multiplied by the sample standard deviation for the first one squared plus the quantity n sub 2 minus 1 multiplied by the square of the second standard deviation, or the standard deviation of the second sample, all over n sub 1 plus n sub 2 minus 2, which is actually the degrees of freedom, no? Given two sample means, multiplied by the square root of 1 over n sub 1 plus 1 over n sub 2. All right, so this is the z distribution. So this is where we find the tabular value or critical value when we perform z-tests, depending on the level of significance and the type of test, whether one-tailed or two-tailed. And then the second one is the t distribution. So here is the possible values for the critical values when we perform t-tests. So the value also depends on the type of test, whether one-tailed or two-tailed test, the level of significance, and the degrees of freedom. So test the hypothesis for the following situation. Example number 1, a teacher wishes to test whether or not flexible learning, or FL, is more effective than the traditional instruction. She picks two classes of approximately equal intelligence. So this is verified through an administered IQ test. She gathers a sample of 18 students to whom she uses FL, and another sample of 14 students to whom she uses the traditional instruction. After the experiment, an objective test revealed that the first sample got a mean score or average score of 28.6 with a standard deviation of 5.9, while the second group got a mean score of 21.7 with a standard deviation of 4.6. Based on the result of the administered test, can we say that the flexible learning is more effective than the traditional instruction? So we verified that by conducting a hypothesis testing. Okay, step 1 is to formulate both the null and alternative hypothesis. So what is a possible way of stating the null hypothesis for the given situation? Okay, so we say that there's no significant difference between the two methods of instruction, flexible learning and the traditional instruction. In symbols, we express that as mean of x, mean x of 1. So that is the average score of the first group being equal to the average score of the second group. So that should be mean x of 1 equals mean x of 2. Okay, so correction. That should be mean bar x of 1 equals bar x of 2. And then for the alternative hypothesis, we say that flexible learning is more effective than the traditional instruction. So that means that bar x of 1 is greater than bar x of 2. So the first sample, the first one, flexible learning is more effective than the traditional instruction. So the difference between the two average scores are not the same, no? So the first one is greater than the second. So this type of alternative hypothesis is suited to a one-tailed test. So how do we determine whether the test is one-tailed or two-tailed? That depends on how you formulate your alternative hypothesis. Okay, so if you express the alternative in this way, let's say flexible learning and traditional instruction are significantly different, then that would give us a two-tailed test. No? So you're just saying that the two are not equal. But since here, we state specifically that FL or flexible learning is more effective than traditional instruction, and we use this greater than symbol. So this implies that the test to be performed is one-tailed test, or that is a test applicable to a directional hypothesis. And then for our level of significance, we set the value of alpha at 0.05 or 5%, meaning the confidence level is 95%. Okay, class, unless otherwise specified, you use 5% level of significance. If the situation is a matter of life and death, for example, in the field of medicine, you use 1%, no? 1% significance level. So that means a confidence level of 99%. Step 3, so the standard deviation given is based on the sample. Therefore, the t-test is to be used. Remember, we can only use z-test if you know the population standard deviation. But in this case, what's given is the sample standard deviation. Therefore, we use the t-test. And then step 4, we have to determine the critical value or the tabular value of t. But first, we must look for the degrees of freedom. So degrees of freedom, determining the degrees of freedom is important, is necessary when performing t-tests. Okay, so for two samples, the degrees of freedom is equal to the sum of the two sample sizes, n sub 1 and n sub 2 minus 2. So we have 18 plus 14 minus 2 equals 30. Then find the tabular or the critical value at 0.05 level of significance for a one-tailed test and degrees of freedom of 30 from the t-distribution table. You can also find a copy of t-distribution table online. All right, so here, to locate the critical value, we have to consider the type of test. So we know that it's one-tailed, and the level of significance is 0.05 or 5%. The computed degrees of freedom is 30. So on the extreme left, we have the values for the degrees of freedom. So you locate that one. And then you get the intersection of the degrees of freedom and the level of significance. And we get the critical value, which is 1.697. Okay. So this one is our critical value. Or that is also the so-called tabular value. And then from the given problem, the values that are specified are the two means. X sub 1 is 28.6 and X sub 2 bar is 21.7. The standard deviation of the first sample is 5.9. The standard deviation of the second sample is 4.6. So based on our previous discussion, we know that the standard deviation is a measure of variability. So the lower the standard deviation, the closer the values are, right? So here in the given standard deviations, we know that the values in the second sample are closer as compared with the scores of the first, the scores of the students in the first group. N sub 1 is 18, so this is the sample size for the first group. And then for the second group, we have 14. So since we have two samples, we use the formula, this formula for t-test, no? Because we are comparing the two samples with one another. The first formula under t-test is when you compare a sample from a population, okay? So the resulting value that we get is 3.602. So this one is our computed value of t. So step number 6, we now compare the computed t value with that of the tabular or critical value. So the computed t value of 3.602 is greater than the tabular value of 1.697. So based on the decision rule or the criterion, if the absolute computed value is greater than the absolute tabular value, we reject the null hypothesis. So the null hypothesis is rejected. So step number 7, the last one, is to state the conclusion, draw the conclusion, and that is based on the hypothesis that is accepted. So since we reject the null, that means we accept the alternative hypothesis. So for our conclusion, we say that flexible learning is more effective than the traditional instruction. Okay, so that is for example number 1. Let's have the second one. Data from a school census show that the mean weight of college students was 45 kilos with a standard deviation of 3 kilos. A sample of 100 college students was found to have a mean weight of 47 kilos. Are the 100 college students really heavier than the rest using 0.05 significance level? So take note here that the data is from a school census. So in statistics, census implies population. Okay, so the data actually came from a population. So this one is a parameter. So data that we obtain from a population are called parameters. So this means that the mean weight of 45 kilos is a population mean. And the standard deviation of 3 kilos is a population standard deviation. Then we have a sample of 100 college students. So this is our sample size, N. And they are found to have a mean weight of 47 kilos. So 47 kilos is our sample mean. So we want to know if the 100 college students are really heavier than the rest. Because take note that the weight of the sample students, the given weight, mean weight of the sample is 47 kilos, and this is numerically greater than 45, right? But we want to know if the difference, so there's a 2 kilo difference between the two means, we want to know if that is significantly different. Yes, there is a difference of 2 kilos, but we want to know if the 2 kilos is significant. To conclude that the 100 college students are really heavier than the rest of the population at 0.05 or 5% level of significance. So again, we formulate first our null hypothesis. So in this case, we say that there is no significant difference between the weights of the 100 college students and the rest of the population. So we are saying that the sample mean is equal to the population mean. The sample mean is 47, right? And the population mean is 45. And then for our alternative hypothesis, we state that the 100 college students are heavier than the rest of the population. So in symbol, that means the sample mean of 47 is greater than 45. So again, since we use a greater than symbol, this indicates that the test is one-tailed test, okay? And the level of significance is again set at 0.05. The standard deviation is based on the population from the census, right? Therefore, the z-test is to be used. The tabular value for a z-test at 0.05 level of significance is 1.645. So this is our critical value. So how did we find that? So from the z distribution I've shown you a while ago, so this is the table. We know that the test is one-tailed and the level of significance is 0.05. So we just get the intersection. So the critical or the tabular value of z for this problem is 1.645. So we get the positive value or the absolute value. So the critical or the tabular value of z does not depend on the degrees of freedom, unlike in the t-test. So the given values in this problem are the sample mean. So that's the sample mean weight, which is 47 kilos. And then the population mean is 45 kilos. The population standard deviation is 3 kilos. And we have a sample size of 100. We use the first formula under z-test since we are comparing a sample with that of a population. So we have the quantity sample mean minus the population mean multiplied by the square root of the sample size divided by the population standard deviation. And the computed value that we get is 6.67. So this one is the computed value. So we already have, we already obtained the tabular value, and this one is the computed value. So we now compare the two of them. So the computed value, 6.67, is greater than the tabular value of 1.645. So again, the criterion or the decision rule indicates that when the absolute computed value is greater than the absolute tabular value, we reject the null. So the null hypothesis is again rejected. Therefore, our conclusion would be based on the accepted hypothesis, which is our alternative. And that means that the 100 college students are heavier than the rest of the population. So yung 2 kilo difference is significant. So there is enough evidence to claim that the 100 college students are really heavier than the rest of the population. Now for our third example, a researcher knows that the average height of Filipino women is 1.525 meters. A random sample of 26 women was found to have a mean height of 1.56 meters with a standard deviation of 0.10 meters. Is there a reason to believe that the sample of women is significantly taller than the others? Okay, let's analyze the problem. So in the first statement, a researcher knows that the average height of Filipino women is 1.525 meters. Isn't it that the first statement is actually referring to the population of Filipino women? Therefore, this value of 1.525 meters is actually a population mean value, or specifically a population mean height. And then we have a random sample of 26 women. So 26 is our sample size. And this group of women has a mean height of 1.56 meters. So this is our sample mean value with a standard deviation of 0.10 meters. So the standard deviation is based on the sample. So we are to compare two groups, a sample being compared to a population, but the standard deviation is based on the sample. Therefore, it's rightful to use the t-test. There is no specified level of significance. I mentioned a while ago that unless otherwise specified, you use level of significance of 0.05. But if it's a matter of life and death, we use a 1% significance level. So for our null hypothesis, we state that the sample is not significantly taller than the other Filipino women. So that means the sample mean is statistically equal to the population mean of 1.525. And then for our alternative hypothesis, we are, based on the problem, we are asked if the sample is significantly taller. So that will be, that's where our alternative will be based. No? So the sample is significantly taller than the other Filipino women. So we are saying that the sample mean is greater than the population mean. So the difference between the two values is significant. And since we use the greater than symbol, we have again another one-tailed test. So we set alpha at 0.05. The standard deviation is based on the sample, therefore the t-test must be used. So this means we must look for the degrees of freedom. For one sample, df is equal to the sample size minus 1. So 26 minus 1 equals 25. So from the t distribution table we used a while ago, we obtained the tabular value for this problem. So for a one-tailed test, degrees of freedom of 25 and 0.05 significance level, the value obtained is 1.708. So one-tailed test, 0.05 level of significance, degrees of freedom is 25. Then we get the intersection and we get 1.708 as our tabular value. So the given values in the problem are the sample mean of 1.56 meters, the population mean of 1.525 meters, standard deviation from the sample is 0.010 meters, and sample size is 26. We use the first formula under the t-test since we are comparing a sample with that of the population. So the resulting computed value is 1.75. So 1.75 is the computed value, and the other one, the tabular value, is 1.708. So again, the computed value is greater than the tabular value, so we reject the null hypothesis. So for our conclusion, we say that the sample is significantly taller than the other Filipino women. Okay. So for our last example on hypothesis testing, a researcher wishes to find out whether or not there is a significant difference between the daily allowances of morning and afternoon students in his school. By random sampling, he took a sample of 239 students in the morning session. These students were found to have a mean daily allowance of 142 pesos. The researcher also took a sample of 209 students in the afternoon session. They were found to have a mean daily allowance of 148 pesos. The total population of students in that school has a standard deviation of 40 pesos. Is there a significant difference between the two samples at 0.01 level of significance? Okay, so analyze the problem. Let's find out what variables are given. So random sampling, the researcher took samples from the morning and afternoon sessions to find their mean daily allowances. So there are actually two samples, no? And then we have their mean daily allowances. There are two sample sizes. And then, okay, what about the standard deviation? So in this statement, the total population of students in that school has a standard deviation of 40 pesos. So that means the standard deviation is based on the population. So this one is a parameter. We are comparing two samples, but the standard deviation is from the population. Therefore, we have to apply z-test. Okay. And the level of significance is given at 0.01. So the question is there a significant difference between the two samples? So we just want to know if there's a significant difference between the two samples. We are not saying that the mean allowance of one sample is greater or lower than the other. So this implies that the test to be used is of type two-tailed test, no? So it's non-directional. So for our null hypothesis, we state that there is no significant difference between the daily allowances of morning and afternoon session students. So the two sample means or the two sample mean allowances are equal. There's a difference, but the difference is not significant. And then for our alternative hypothesis, we state that there is a significant difference between the daily allowances of morning and afternoon session students. So in symbols, we write mean x of 1 is not equal to mean x of 2. Take note of the inequality symbol. We did not use the greater than or the less than symbol. Instead, we have the unequal sign. Therefore, that means we have to perform a two-tailed test. Okay, so the type of test, whether one-tailed or two-tailed test, depends on how we formulate the alternative hypothesis. So we're given a level of significance of 0.01. Again, the standard deviation is based on the population, therefore the z-test is to be used. The tabular value for a z-test at 0.01 level of significance is 2.58. So this is based on the z-table. At 1% level of significance of a two-tailed test. Okay, so the given values in the problem are mean x of 1 equals 142 pesos. Sample size 1 is 239. Mean value for the second sample is 148 pesos. And then the sample size for the second group is 209 with the standard deviation, population standard deviation of 40 pesos. So that's the formula to be used. So that is for Z comparing a sample with a population. So the computed value is negative 1.58. But when we compare this with the tabular value, we have to consider the absolute value. So the absolute computed value of negative 1.58, so that is positive 1.58, is less than the absolute tabular value of 2.58. Less. Therefore, when the computed value, the absolute computed value is less than the absolute tabular value, we accept the null hypothesis. Okay, so this time we do not reject the null hypothesis. So that means our conclusion will be based on our null hypothesis, and that is there is no significant difference between the daily allowances of morning and afternoon session students. Okay, so we have another example. A sample survey of a television program in Metro Manila shows that 75 out of 250 women do not like a certain TV program. Out of 200 men, 80 dislike the same program. We want to decide whether the difference between the two sample proportions, 80 over 200 and 75 over 250, is significant or not with regard to TV viewership of this program at 0.05 level of significance. When comparing two proportions, we use z-test. So we use the formula of z-test for comparing the two proportions. So for our null hypothesis, we state that there's no significant difference between the two sample proportions with regard to TV viewership of a program. So that means P sub 1 is equal to P sub 2. And then for our alternative hypothesis, we say that there is a significant difference between the two sample proportions with regard to TV viewership of a program. So in symbols, P sub 1 is not equal to P sub 2. So again, since we use the not equal symbol, this means that we have to perform a two-tailed test. The level of significance is set at 0.05. So again, we use z-test to compare two sample proportions because t-test has no corresponding formula for comparing two sample proportions. The tabular value for a z-test at 0.05 level of significance for a two-tailed test is 1.96. So you just verify that from the Z distribution table. So the first proportion is 80/200, and that is 0.40. So Q sub 1 is 1 minus 0.40, and that is 0.60. P sub 2 is 75/250, or 0.30. Therefore, Q sub 2 is 1 minus 0.30, and that would be 0.70. The sample size for the first group is 200, for the second group, 250. And this is the formula that we used. The computed value is 2.21. We now compare this with the tabular value that we obtained. And note that the absolute computed value of 2.21 is greater than the absolute tabular value of 1.96. Therefore, that means we reject the null hypothesis. So for our conclusion, we say that there is a significant difference between men and women TV viewership of the program. And that ends our discussion for today.